Okay, welcome to the Atomic Pod. This is an emergency broadcast. We are coming at you because something incredibly important has happened in the scientific community, and we wanted to talk about it today because of how huge it is. There was a paper that hit the internet, hit the preprint archives a little over a week and a half ago or so. There are laboratories all around the world, really, that are trying to replicate the results right now to fabricate a room temperature ambient pressure superconductor. So we're going to break down for you guys what that means, what the implications of that could be, and what we think is going to happen with this, because we cannot stress enough how important this would be if it worked.
David, what do you think is LK-99 and why do you think everyone is hyped up? Like, what's the big deal? Even if this is a superconductor, okay, what does a superconductor mean, first of all? And apart from that, what exactly can we achieve by actually having a superconductor? And what does it mean for, the average Joe who doesn't really want to understand a lot in physics and chemistry? Okay, why should someone be worried about it?
You might not think that this would affect you if you are not one who cares too much for developments in the physics world, in the physics community, in the science community. Um, we all use tech whether we like it or not. It's a part of our lives. And the reality is that room temperature superconductor would change everything about the way that we engineer electronics. The entire kind of crux of the engineering problem is that you have to overcome electrical resistivity. And superconductors allow you to mitigate the resistive properties of the metals that we use as semiconductors, as materials that we use for computing. So this eliminates not only the need for cooling fans, but beyond that, has implications for nuclear fusion, for magnetic levitation trains, for all these areas of technology and the way that we approach electrical engineering. Superconductors, this is LK-99, named for Lee and Kim, and 99, the year that they first synthesized it. There are now teams all over the world who are trying as fast as they can to replicate the results and publish research to confirm that LK-99 is the room temperature superconductor of the future.
That's interesting. And so the whole point is see, we are trying to understand what exactly is meant by a superconductor and what are the implications. So when something like this comes across, it is actually in the category of too good to be true. So the traditional process is that when something like this comes up, then you have scientists across the world in the field of physics and chemistry trying their best to replicate something like this, because the commercial implications of replicating something like this are huge, absolute huge. So let's do one thing, David. Let's talk about what exactly is a superconductor and why exactly is this room temperature concept very important, because I believe a gazillion objects are room temperature. Why exactly is a superconductor being room temperature important enough?
Right. I mean, it's the most important thing in terms of
Of
electrical
course.
engineering. And when you see a title like this, the first room, when you see this title is like hey, give us a Nobel Prize, or give us all a bunch of Nobel Prizes. And if it turned out to be true, there wouldn't, everybody involved would probably be getting Nobel Prizes, because this is so tremendously important. And the big thing is the Meissner effect, right? We want to see the Meissner effect present with the samples that are being produced, and that's what people are going to try to reproduce to either prove or disprove the claims that were made in this paper.
See, when we talk about something being a superconductor, first of all, there are three levels of something being a conductor. So there is a conductor, something that conducts electricity very easily. Generally, these are your metallic objects like copper, gold, aluminium, silver, multiple objects. Now, when you go one step further, then you have something that is an insulator. So something that will not conduct electric current at all. This is your plastic, this is your cloth, this is to a certain extent water. These type of elements do not conduct electricity. This goes into the insulator category. Now you have something in between. This is called as a semiconductor. As we choose to create transistors, or as we choose to create electronic objects that can act like a switch, like it can be on or off based on the available conductivity expectations from that element, then it becomes very interesting, because by using something called as a semiconductor, where you have the ability to make it behave like a conductor or like an insulator, this opens up a whole new world, because suddenly now you have modern computing, now you have chips, now you have transistors. Now, in the domain of these three types of conductors, we have something else on the far left spectrum. Now, this is called as a superconductor. Now, the point is, we need to understand what is defined by conductivity. So, when you say that something is a superconductor, or when something is a conductor, it means that electrons or electricity can pass through it with very little resistance. When something is an insulator, electricity can still pass through it, but with a very high resistance. This is why you would have seen something in the case of lightnings, or in the case of Tesla power walls, that you have very high voltage electrodes. Once these electrodes come in, you have sparking. So generally, electricity can flow across anything, but in case of insulators, the resistance is so high that it becomes impractical for electricity to flow for any normal applications. Now, if you look at the far left spectrum, then you have something like a superconductor. Now, this superconductor is where you have zero resistance for electricity to flow. This is absolute zero resistance. Now, this is very important, because this means you have no loss in electricity flowing across the superconductor. And the whole point is, you don't have any efficiency problem. So, this is like operating at 100% efficiency. So,
Right.
generally, when electrons flow through a particular metal, they have to bang, or they have to make their way through the atoms inside that element. In case of superconductors, that's not the way, because every atom is stationary, every atom is stable, every atom is not moving inside that element. So electrons can flow very easily. So in a nutshell, see, that is superconductors. Now, if you were to look at the properties of something like this, then superconductors are first of all having zero resistance to the flow of electrons, to the flow of electricity. The next part is electrical current and magnetism are correlated if you go through the Faraday's law. So, when you have something that is having very low resistance, it means that it behaves very interesting in the magnetic fields. So, superconductors are generally diamagnetic, where they repel magnetic fields from both their sides. So, generally, if you look at any metallic element, it is either attracted to a magnet or repelled based on the poles that it is facing. In case of superconductors, both of the poles of these magnets can repel each other. This is something that is found only when atoms settle down at a near zero velocity. And this is what David was mentioning as the Meissner effect. So now the whole point is, all of this coming together is very important. So if you think about the game, the whole point is, if you want to decrease the movement of atoms within that element, like every atom is banging against each other, that's how they create these covalent bonds, the ionic bonds. If you want to decrease that, generally the way to do it is in two forms. So either you put very high pressure on the element. So this very high pressure is in the domain of gigapascals. When we say gigapascal, 1 gigapascal is a few million times higher pressure as the atmospheric pressure we are experiencing on Earth. Or another way to do that is lower the temperature. When you lower the temperature, the atoms start stabilizing. Like the cooler you go, as you start approaching absolute zero, that is when these atoms stop moving. So again,
Absolutely.
due to some physics macaroni, due to some physics soup, absolute zero is not possible. You can just go as close to it as you want.
And it's
So
also not the
yeah,
natural state of things, right? Things don't exist at that temperature in
exactly.
our normal everyday life. So it takes an inordinate amount of energy. You have to create a system basically in order to cool the environment, the system in these in a physical standpoint, cool things down so that you can reach this these properties that of extremely high pressure, extremely low temperature, where the atoms are basically immobilized and the electrons are just jumping kind of across in a quicker fashion.
If you think about this a little bit further, even space is very far away from absolute zero. Like if you go to the depths of space, that is still a few billion times warmer than absolute zero.
It's extremely cold, and I think that people, you think, oh yeah, okay, pretty cold. No, this is extremely, extremely cold that it has to be in order to in order for materials to reach this to achieve this property. And so that's what makes this so interesting is that if we can conceive of a material that doesn't require all of this energy intensive refrigeration to cool the system down to negative, you know, to negative 273, that is huge. That has tremendous implications, and Department of Energy, you know, lots of people will be interested and are following these developments very closely.
If you look at it, if humanity has potential or even has a way to manipulate the behavior of atoms at such a minute scale, that opens up a whole new world of studies. It's like the best merger between physics and chemistry that you can think of, first of all. And then it helps you completely redefine electrical engineering or even any electrical system. So, David, let's take a moment here to understand what are the stakes here. Like, okay, if suppose we are able to generate superconductors at a mass level, what does it mean? Like, why is it even important at all?
Absolutely, that's it's a great thing to establish so that everybody can understand. Think about this. These are a few notes from Alex Kaplan, who's been vocally discussing this on Twitter. He writes, a billion kilowatt hours are wasted on transmission losses each year in the U.S. alone, which is equivalent to 3 of our largest nuclear reactors running 24/7. So superconductivity would enable completely lossless electricity transmission even at high voltages and currents. So that's number one, is the efficiency of electrical systems, which is always a struggle for anybody who works in electrical engineering knows this is your main public enemy number one is the resistivity. So you can take this and run with it if you are able to overcome that barrier. Superconductivity completely eliminates the loss that you have to deal with. The other thing is that it doesn't even. It's interesting because the procedure to prepare the actual material. Apparently, the material can be prepared as little as 34 hours. Relatively basic lab equipment. We're talking about like mortar and pestle, basic vacuum, and a furnace, and taking days to weeks to replicate. That's why you've got Argonne National Lab. You've got all these people who are racing to try to replicate the results right now. Also, things like magnetic levitation trains, electronic MRI systems, and quantum computing. Quantum computing is the biggest thing. Again, with quantum computers, is everybody wants to see a room temperature superconducting qubit. Could be the thing that pushes us over the hurdles of kind of the material science, the materials engineering that is holding up the development of quantum computing systems.
If you if you extend it from there, see, the fact that you shared about the world losing a huge amount of its daily power requirement just in transmission is crazy.
It is
Because
wild.
once you
Yeah.
start thinking about it, this is actual energy that could be used to power applications. So,
Right.
energy independence is a huge thing. Countries fight wars over energy, countries fight wars over oil, over basic commodities which are used to again generate energy. So, energy is a huge part of our daily life cycle.
We destroy
Now,
the environment in order to generate it. I mean, and
exactly.
to
And
think
then
that
you
there's
spend
so
extra
much
in just
waste,
transporting it. So,
and
that's crazy.
it's just gone, and we have just this level of acceptance. We say, well, that's just the way it is. This is why the LK-99 this development could be so monumentally important, is because these conventions that we've just kind of had to accept as, well, it's just the way it is. You just have a lot of loss. We make a lot of energy. We lose a lot of energy on the way distributing it. That's crazy. If we could eliminate that, it's actually it's kind of gross. To think about the way that we just fossil fuels and we have just destroyed our environment, and we the way that we distribute the electricity that we produce is so radically inefficient that it boggles the mind. So this is incredibly important.
Absolutely. And see, from there, the main loss behind energy transportation is in the form of heat. If you have seen any computer application, if you hold even a laptop in your hand, it's generally warm to touch when it is switched on. The whole reason why this is happening is that electricity is converted into multiple forms. It is used to operate a lot of transistors. These transistors generate heat. This heat has to be dissipated in some way. That's why you have these fancy cooling fans. That's why you have fancy cooling hardware. That's why you have efficient systems that promise on generating less heat. But again, the whole point of having heat in these systems is because our traditional computers or electronic systems use semiconductors. Now, semiconductors again are either an insulator or a conductor, but they are not very good at being both. So it's
Right.
something that comes in between. So now, if you have superconductors in this place, this could open up a whole new domain of possibilities, because now suddenly you don't really have to worry about extra heat being generated from your devices. You don't have to worry about cooling all of that. Then you can just so something, if it is operating at 5 gigahertz right now, if your laptop is operating at 5 gigahertz, the only reason why you cannot bump it to 50 gigahertz or 500 gigahertz is because it will generate crazy amount of heat, and there is no way you can dissipate that. So if you have seen these videos where they overclock processors to like 7 8 gigahertz, and then they have to run liquid nitrogen through it.
Otherwise,
So
it'll burst
this
into
is the
flames. Yeah.
exactly, someone has actually cooked an egg on a CPU processor while it is doing some compute intensive task. So this is the level of energy loss that we are experiencing through traditional systems. So again, superconductors could help you build computers or build electronic systems that you could have never imagined before. Then finally, we have maglev trains, where once you have trains, a lot of energy in these trains is gone into overcoming the friction between the rail and the train chassis. Now, in case of maglev trains, there is absolutely no friction. These trains are levitated, and then you just find a way to accelerate these through magnets in the tail track, and it goes very fast, because these trains are not touching any, there is no moving part, because it is levitated. In that sense, there is theoretically no limit in the speed you can achieve. And then finally, we could get very high definition MRI machines. Right now, the most powerful MRI machine is about 15 to 20 Tesla. Tesla is a unit in which we measure magnetic field. So right now, just imagine the whole reason why we cannot go from a 15 Tesla MRI machine to a 100 Tesla MRI machine is again because of the heat. So you need to have very powerful magnets in the circuit, and to actually have these very powerful magnets, you need to accelerate electric current to a very, very high velocity. Again, this is not possible because of the heat generated by the system. So if you track everything down, it kind of comes down to the inefficiencies between transporting electricity.
It all comes
And
back to the
again,
efficiency. That's like
exactly, and
the kind of the
a
overarching
10
theme.
times having a 10 times more efficient MRI machine is the difference between life and death in certain situations, because if you have a very high definition scan of someone's brain, that could give you details which you might have missed.
Absolutely. Another thing that I thought was interesting that I had heard was that superconductors could make incredibly efficient batteries. You simply inject a current, keep it in coil until you need it, and up until now, any kind of superconductor based battery technology would have just been too completely expensive and costly to maintain. All of a sudden, this could become totally feasible. And again, I think the kind of the overarching theme is around efficiency and kind of the conventions that we've been forced to kind of accept in electrical engineering.
Cool. Let's move on from talking about Teslas. Of course, not the cars, not Elon, but about magnetic Teslas, which come from Nikola Tesla. Let's go to something that has more far-reaching implications in terms of having superconductors on board. Now, David, uh, while we are here, I want to hear your experience in the quantum computing space. I'm sure you have had your hands dirty for a long time. I want you to summarize for the listeners. Okay, first of all, what are quantum computers? What exactly is, why do you need superconductors for it? Why is it relevant here? And then currently where we are.
Absolutely. So the existence of a quantum computing a quantum computing processor or a QPU, it's one of those things that is a engineering paradox. You have to create a system that is impervious to outside influence that you can still control, meaning influence from the outside. This is a this is a paradox, clearly, and it is one that we have only been able to overcome by using extremely energy intensive systems to cool materials down to extremely low temperatures to create this superconductivity state, and that allows basically the operations to be done in such a way that they are so efficient, and they can perform these operations reliably. The problem is that they're still too sensitive, so you still have a high rate of errors that occur because they're not perfect. They're not perfectly insulated from the outside world. They're still even though we can cool it to extremely low temperatures, these qubits can still be influenced by you know any source of entropy, whether it's the friction from moving your mouse or ambient solar radiation that's just kind of vibrating around the room. It's near impossible to tell what the source could be, but it results in a much higher rate of error than we'd like to see in order to use quantum computers as a practical tool reliably. And that's what the entire quantum computing world is holding their breath, waiting for that error rate to either drop off or to come up with some type of error correcting, fault tolerant method to control the technology. This is will be completely upended if the LK-99 phenomenon is proven to be true, to be a real room temperature ambient pressure superconductor. This would allow us to build incredibly accurate and incredibly efficient quantum computing systems that would be much more feasible to implement into enterprises in a cost effective way, because you look at things like the D-Wave machines, which are my favorite quantum hardware. Those guys have been doing it, if not the longest, they've been doing it, in my opinion, the best job with dealing with these issues, with creating technologies that are actually applicable. And what they've done, if you look at the size of the chip, you can't really tell from this picture, but it's actually incredibly tiny. I'm talking barely in the palm of your hand. And the housing for it, the box, if you look at what the box looks like, it's massive. It takes up half of a room. It's huge. The picture doesn't do it justice. It's bigger than you could have people standing next to it, and it would look huge, because you have to have all of this refrigeration technology in order to house and case the qubit. And that is why it is so crucial. That's why the quantum computing community is so excited about the possibility of LK-99 being a potential boon to this engineering problem, where we can achieve superconductivity at room temperature.
I had a fair stint in quantum computing. I have been an instructor on various quantum computing topics. I've worked with a couple of folks in a consultancy way in multiple quantum computing projects. As far as I understand the space, the limiting factor behind how big or what type of computing you can achieve is the amount of qubits. Now,
Right.
the qubits are again have to be in a quantum entangled state. Now, again, this is a whole different session, and we would most probably link a separate episode to quantum computing and its wonders. But generally, it has to be in some sort of high order state, like the qubits have to be. And in order to maintain the state, there has to be absolutely zero noise in that element. When I say noise, as David said, it's anything from solar radiation to atomic vibrations to electromagnetic radiations. Even the Wi-Fi signal is a million times more powerful to damage everything inside. So for quantum computers to be applicable in any certain scenario, we need superconductors, because by the definition superconductors have absolute zero atomic vibrations. So suddenly if you have superconductors, you could have quantum computers with 20,000, 30,000, 100,000 qubits, and that could open up something totally new. If you think about it, this is very similar to the state of silicon. So before the advent of modern silicon, we had like vacuum tubes, or we had transistor chips. So like actually having a vacuum tube was very difficult, because that had to be, of course, as the definition says, in vacuum, and then it operated at a very high temperature to ensure that it can act as an electronic switch. Now, when you talk about something that is being like an electronic switch, the byproduct is that 99% of the energy spent is spent in heat. So it used only 1% of what it was supposed to do in actual, like its actual function. But the moment we had modern silicon, where okay, you didn't need all of this heat, you didn't need the expensive hardware like the glass vacuum tubes, suddenly you could just have a very simple chip. On this chip you could have like a few million transistors, and that's it. Suddenly this opened a completely new space where now you could do computations like never before. Now you could store a lot of data in a very small footprint, and it was just the advent of the modern computing era. So think
Right.
about it. If we are talking about a similar revolution in terms of quantum computing, where something so fundamental changes, and now you can have quantum computers that are actually working at room temperatures, that are actually that is something that you are able to just turn on, start working on it, shut down, take it along with you. That's a completely new way,
And
and
not
that could
just 10 or 20 qubits. We're talking about tens of
exactly.
thousands, hundreds of thousands of qubits, which is what we've been waiting on, right? In order to make these, to make QPUs actually usable. The applications, what everybody's waiting for is to model extremely hard problems, lots and lots of different
Yep.
variable outputs. In order to be able to build a system like that, you need lots and lots and lots of qubits. And again, we run into this problem where the error rate, because of noise, it's just too high to really be useful. And so that is why we are also excited about it. Vinay, you did a great job, really kind of zeroing in on what this means, and I am so excited about it.
Cool. So before we segue into our next broad application of uh, superconductors, I just want to open up a can of worms. So just think about it. If you had a 2000 qubit system, or let's say something in the range of 20 to 30,000 qubits, you could model every single DNA strand out there. That means no virus, no no disease, no fungi would be unsolvable. Suddenly you could just take a quantum computer, simulate like a gazillion different drugs on a virus type, and then come up with the best sort of drug. So drug discovery could be changed completely.
Absolutely, mRNA therapies and our entire understanding of genomics would totally change overnight. Talk about our
Exactly.
we I don't remember what year we sequenced the genome, the Human Genome Project. That was monumental. Deep fold, alpha fold, these deep mine, excuse me, alpha fold. I mean, this was a massive step forward in our ability to understand protein folding dynamics and how we can actually think to engineer proteins and things like that. This is even a step beyond, many steps beyond, where we could literally have complete control over simulation of human genomes and drugs and everything, just because we have more, you know more control over variables in the simulation, so you can build an incredibly accurate and detailed simulation. That's really the where everything gets lost in the cracks, right? Is like we study all these different subjects and we build simulations, we build models to model them, but the model always fails to take into account some level of detail. So when you have tens and tens and thousands, tens of thousands, hundreds of thousands of variables that you're able to track and compute all of them in real time, in instantaneous time, that is the
That
impact of
is,
that
it's mind
cannot
blowing.
be. It's mind-boggling. It's
Yeah.
absolutely mind-boggling, and we are so excited about this. We want to believe. we we want to believe in LK-99 very badly.
All right. So moving on to the next broad application of superconductors. It's of course made a lot of buzz recently, not because of the superconductor space, but generally because someone claimed to have a net zero output. So, David, for the average listeners, can you summarize what is nuclear fusion and why is it important at all? Why should someone focus on it? And maybe walk us through why are superconductors important here?
Absolutely. So nuclear fusion, nuclear fission, the way that we are generating an out a net aggregate output of energy from these systems is we are basically colliding particles at extremely high speeds so that they either fuse together or break apart because of the intensity of the collision. So the force that is binding these subatomic particles together is extremely powerful. It's so powerful that it is when you're able to break or break these bonds and create these reactions, hopefully only requiring a small amount to put in. So that's the promise is this can be more efficient than burning coal, than burning fossil fuels. That's why we want this technology to exist, is because we want to stop burning fossil fuels. We want to be able to do this and produce massive amounts of energy in a way that is clean, that is good for the environment, that doesn't produce a lot of harmful waste and byproducts. And so, if we're able to create nuclear reactors that are efficient, that don't require a massive amount of energy to run, that are able to create a massive amount of energy to put out and use as usable electricity, that's wonderful. That's what we want. So the higher the performance, the better. The more excited the science community is going to be about it. We talk about a Q value. The Q value is over. If Q is over 1, that means that more energy came out than was put in, and that's what we're hoping to achieve. So one of the challenges to reaching that value is superconductivity. So in order to confine the plasma that is created with these particle collisions, we use extremely powerful electromagnets to magnetically confine the plasma so that we can sustain a reaction long enough to take energy out of it, or the magnets, electromagnets, down enough to the point of reaching superconductivity. That takes a lot of energy, and that is going to hurt you when you get to the end and have to tally up how much energy do we put in and how much energy came out. Well, if you had to use a lot of energy in order to cool the system down, that's going to be a higher hurdle for you to jump over to say, hey, look how much energy we took out of it. So that's why LK-99 is really exciting in terms of implications for fusion and for fusion reactors, because if you're able to sustain the superconductivity in the confinement electromagnets without using a whole bunch of energy, then it's going to make it a lot easier for you to say, hey, look how much more energy we took out of it than we had to put in.
Building a nuclear fusion reactor is exactly the same step to replicating a sun on Earth. So, if you think about it, the best example of nuclear fusion is what happens at the core of the sun. So, you have hydrogen being converted to helium, and that generates a lot of energy. Now, in order to make something that is sustained in a nuclear fusion reactor, you need to make sure that you reach very, very high temperatures. It's the exact same process of, again, as I said, replicating a sun on Earth in a confined way. Now, this is where the Q value comes in. Like, okay, you have spent certain amount of energy to create an environment like the sun, where you have very high temperature, where you have very high pressure, and you have the full ecosystem ready. Now, you have spent some energy in creating an environment like this. Once you have spent this energy, you need to understand that whatever you're extracting out of the nuclear reactor is more than what you have spent in. Now, the majority of the energy that is spent in these nuclear reactors is again in the process of generating dual electrons. Now, why do you need dual electrons? It's the only way in which this reaction can sustain. So, electricity is like the flow of electrons. So, once you have created one electron, the whole point is getting it at a very high speed so that it goes and it bangs into a new atom. In this new atom it can generate two electrons. So the second one is used to generate electricity, and the first one is again used to continue the reaction. So this is how, as David said, you have one, then you have two, then you have four. So that's how it becomes an exponential reaction. Now the fuzz behind having superconductors is again because once you have actual room temperature superconductors, suddenly making very high speed electron accelerators is not difficult at all. And now once you have very high speed electron accelerators, nuclear fusion suddenly is possible to a very huge extent. And once nuclear fusion is possible, it essentially means that we are in a world of energy abundance. That is like an upgrade button for the full civilization. Once you hit energy independence, it's like, okay, new level unlocked.
It's absurdity. It is complete absurdity when you think this literally solves all scarcity, all energy scarcity. This solves world like every single societal problem that we face as the human species overnight goes away because we're able to create limitless energy for next to no cost. I mean, it is the most profound thing that could ever happen if it is real. So that's why we have to talk about this and we have to follow this closely because we need this. This is a win that we need desperately at more at no point more in history than now do we need this to happen. So yeah, it's it's huge.
David, you mentioned that we are losing a lot of energy in transmission of power from one city to another. You can actually improve on this efficiency by 50% by just making wires out of gold, solid gold.
Right,
Why don't we do that? Because it is not economically viable.
right.
So it's like creating wires out of gold, like the economics behind it are far less worth than actually losing out on the energy. So, see, the technology is there. The only point is it has to reach a stage where it is commercially viable.
Right.
So, again, if we are thinking about it, having a room temperature where something that doesn't need to be cooled and a standard pressure, like 1 atmosphere pressure, is a new type of element where if we are able to synthesize this particular alloy or this particular ligand, where we have a room temperature superconductor, again, this opens up all of these possibilities. So, while we are here, David, I would request you to just kind of summarize where are we on this attempt? Okay, where exactly is the world headed? Is it something that, okay, tomorrow we can have industries producing gigatons of something? Is that possible? Where are we? What are the next steps?
So, the exciting thing is that it sounds like if taking the paper at face value, what they're claiming is that it is super reproducible, and that this is something that you can manufacture cheaply. This is it's not as expensive as mining gold, or as wouldn't anger people as much as, hey, give us all your gold so we can replace the whole wire system. This is something that you could just fabricate relatively cheaply in a simple lab, and could really be like a highly democratized technology. um, the issue is that we are watching all these reproduction efforts very closely, and we are seeing people maybe see a little bit of diamagnetic properties, but not what I've seen is not fully looking like Meisner uh, to me. But seeing for me, seeing the video, I think of the actual experiment that the team put out. That was where I don't think it really looked like Meisner effect to me. I think it looks probably more like it has magnetic properties. But there are many teams all around the world who are trying to reproduce this right now. There was also a little bit of, another thing that kind of calls this into question that we have to, approach with our kind of skeptic's eye is say, there was a little bit of drama around the release of the preprint paper. So Lee and Kim et al., which LK, Lee and Kim, and then, but there was a third author, Kwan, who was the one who actually posted the first that paper on the preprint archive. And then shortly afterwards, there was another paper that was posted by a different one of the authors, um, which had similar claims, but I think it was the second paper had kind of backed off a little bit. So it's showing levitation, but they didn't actually show the drop off of the resistivity going to zero, I think. And so that was what they really needed to see. They showed the conductivity increasing, but they didn't show the resistivity drop to zero. And so that's what we really, really need to see, right? Is that at a ambient temperature, the resistivity is at actual zero. So we're still waiting for the smoke to kind of clear there. Although there was, I believe it was in March, there was filed a international patent, and the paper that went, and it was also published in a Korean journal. Um, but that paper is in Korean, and I cannot understand it. So I couldn't really make my way too far through that, but I did read the abstract. Like I said, still a hot topic of debate. So we are we are optimistically, but hesitantly excited about this development, and are very eager to see what happens with all these replication attempts.
All right. And so generally, see, let's dive into these replication attempts a little bit, right? So you have a lot of universities, a lot of commercial organizations trying to replicate. And generally, what you're looking for is levitation, diamagnetism, and finally an XRD match. So an XRD match is just like matching the exact atomic structure. Then magnetization is where you actually understand if the whole element is being diamagnetic or not. Basically, is it repelling magnetic field from both sides or not? And then even if you were able to achieve this, the next point is it showing levitation? So if all three points coincide properly, if you even go to the earlier attempts where they have shown partial success, again, the whole point is they were able to synthesize a few grams of the element. Now, again, doing this at a commercial scale might be very, very difficult. So, yep, for our listeners, that's where we are on superconductivity. I'm personally rooting for superconductivity to uh, be the next big thing. I'm personally very optimistic. I'm hoping that this could revolutionize the way we even engage with the physical world, and hopefully, this could be the new upgrade button for the human civilization. We don't know where
Absolutely.
this is headed.
I think superconductivity definitely is going to be the future. To me, the question is just: is it LK-99, or is it going to be a different compound? Right now, for me, I think it comes back to the uncertainty around the strength of the diamagnetism. If it is creating repulsion, is it repelled by a lot? Is it is it a strong diamagnetic, or is it a weak Meissner effect? That's kind of the edge of the knife that blade that we teeter on right now.
All right, cool. So, for our listeners, thank you so much for taking out the time. We wanted to shed some light on where the world is headed towards LK-99, towards superconductivity, towards generally understanding how electronics work, towards understanding how material science works. Hopefully, we were able to shed some light, look at facts in an unbiased way, and give you our opinion. So, thank you so much for taking out the time. The next episode is going to be very interesting, where we'll be talking about a very interesting physics based phenomena. So, all right, thank you so much for taking out the time. David, any closing notes, or should we roll out the intro?
No,
outlook.
I'm with you. I just want to thank everybody and thank you, Vinay, for doing this. I really enjoyed this emergency LK-99 update, and can't wait for the next one. And I think this was a good segue into our talks about quantum technology and quantum computing. So excited to get into all that as well.